Good afternoon, everyone. Thank you for attending today's webinar. The topic today is 950 megahertz networking with Intraplex HD Link. After a brief introduction on the 950 megahertz band, we look at the three main sections of HD Link. We'll start off with the RF and modem section. We'll then look at the services area, the services that HD Link transports, such as audio, Ethernet, and how it relates to the QAM level. And finally, we'll look at the networking section, which deals with transport of those services over both RF and IP path. We will also have a brief look at the web interface of HD Link to look at how some of the things we discuss today in the presentations are configured. We will take questions at the end of the presentation, so leave your questions in the live chat. Thank you. So the 950 megahertz band is used in the US, Canada, Brazil, and several other smaller countries in Latin America. In the US, FCC Part 74 reserves the frequencies in the range of 944 to 952 for broadcast auxiliary services, or BAS, and it's licensed in studio to transmitter direction, the channel by kilohertz with several selection for channel bandwidths from 200 to 500 kilohertz. The first generation systems were analog systems and were primarily used to transport analog composite FM signals. The move to digital was primarily driven to add more channel capacity and to support Ethernet data for HD radio, specifically E2X stream or exporter to exciter streams across the STL. The capacity requirement, specifically the user data capacity requirement for digital STL, depends on the services that you want to transport. For E2X, you typically need 256 kilobits per second, but because of the bursty nature of the pattern of the E2X stream, you typically end up allocating about 330 kilobits per second. For audio channels, the data rate depends on the encoding format and the sample rates. For example, for a linear audio with 32 kilohertz sample rate with 16-bit sample width, you need about 1 megabits per second. Higher for 44.1 sample rate. Compressed audio or compression can reduce this requirement, and HD Link supports aptX compression, which provides 4:1 compression over linear or uncompressed audio. And if you add additional audio channels or RS-232 for RDS, for example, the capacity requirement goes up. And we'll take a look at this in more detail in the upcoming slides. So HD Link is a digital STL system with the following key capabilities, and we'll look at this in more details as we go on. It has advanced RF and modem capabilities, flexible services that can be configured from encoding format of the audio cards to using the system as Ethernet radio, where all the RF capacity is allocated for Ethernet services, typically used in conjunction with IP Link codecs to transport audio or FM MPX signals. It has a transport redundancy with both RF and IP path, and the system can be configured as a single hop or a multi-hop using a repeater configuration. Let's start looking at the three main areas that we talked about. We'll start off with the RF and the modem section. The frequency range supported by HD Link is from the range of 932 to 960 megahertz to satisfy both US and Canada. There are 5 different channel bandwidth configuration from 200 to 500 as shown here, and the integrated PA can be set to 1, 2, or 5 watts. On the modem front, it is a single carrier system as opposed to a multi-carrier system such as OFDM with support of multiple QAM levels from 32 to 256. Obviously, higher the QAM level, higher the data rate you can accomplish, but requires higher signal to noise ratio. And we'll go over the actual numbers in the upcoming slides. The modem uses LDPC channel coding for protection of your RF bit stream. LDPC is superior to Reed Solomon by about 3 dB, so you have about 3 dB of additional system gain. And for ease of usability, the system will automatically select the optimal QAM level and the channel coding overhead for the protection, based on the user data rate requirements, which in turn depends on the services that you as a user select and the channel bandwidth that's selected. So this chart shows how HT-Link provides better system gain or receiver sensitivity using combination of LDPC channel coding and higher PA power. For example, if you compare the 1 watt LDPC system to 1 watt Reed-Solomon system, that's the first two bars here. You get 3 dB of system gain, and as you add additional power, your gain goes up. And with HD Link, you get up to 5 watts of power, and you can see the last bar. You can get about 9 dB of additional gain as compared to the 1 watt Reed-Solomon system. All in all, though, if everything is equal, LDPC provides 3 dB of additional system gain. That's the key takeaway from the slide. So HT-Link supports several RF and modem performance matrix at the receiver. The front end receive level measures the energy in the 5 megahertz band around the channel. So this is what we call the wideband level. A low signal to noise value at the receiver with a high front end level, can indicate adjacent channel interference. And for adjacent channel interference, you may need to install an external bandpass filter to notch out your channel. Then you have your normal receive level, which is centered around the channel that you have selected. Again, a low signal to noise ratio with a high level of receive level, indicates a co-channel interference. And for co-channel interference, you really have to just track down the interferer. But the most important metric as far as HT-Link is concerned is signal to noise ratio. It comes directly, from the modem ASIC. It measures the fidelity of the QAM symbols. And the highest value for the SNR that the system will report is 36. So this would be in a bench setting with the optimal receive level. The minimum requirement for signal to noise ratio also varies based on the QAM level and the channel bandwidth. For example, the table here shows values for a 500 kilohertz channel. As you can see, for 256 QAM level, you need minimum 26 dB of signal to noise ratio. Below this, the modem will unlock, and as you reduce your QAM level, your signal to noise ratio requirement also relaxes a bit, 24 for 128, and so on and so forth. Again, these are the absolute minimum threshold. Below this, the modem will unlock, as I mentioned. And so you do want to operate with a fade margin, and we recommend at least 6 dB of fade margin above the minimum required threshold, in the table that's shown up. So for example, with 256 QAM at 500 kilohertz, you would want to operate with 32 dB showing at the receiver or higher. Similarly, for 128, you want to operate at 30 dB or higher. So what is the total user data rate capacity? Well, that depends on three things: channel bandwidth, the QAM level, and the channel coding overhead to protect the RF bit stream. But keep in mind, as a user, you only select the channel bandwidth and the services that you want to transport. The system will calculate the total service rate requirement and select the most optimal QAM and channel coding, as I mentioned earlier. But the maximum user data rate that's accomplished with HT-Link for a given channel bandwidth is shown here in the left. For 500 kilohertz channel bandwidth, you can get maximum of 3.2 megabits of user data rate, and for 300 kilohertz is 1.8, and for 200 is 1.2 megabits per second. The table on the right, the user QAM overhead, for 500 kilohertz channel, we have similar tables, for all the different channel bandwidth we support. So you can see that the maximum user data rate occurs in the first row of 3.2 megabits per second. That happens at a QAM level of 256, which shouldn't be surprising, and the overhead, the channel coding overhead of 10%. So with such a low channel coding overhead protection and 256 QAM, you really need a pretty good RF link to sustain 3.2 megabits per second. And you can see in the last column, the signal to noise ratio kind of implicates that you need minimum 26 dB of signal to noise ratio. And as you increase the the channel coding overhead with the same QAM, your user data rate uh, goes down because you're spending more of your total modem bits on the protection. And as you go down in the QAM level, your user rate also goes down. As a result, all your signal to noise ratio requirement also relaxes, from the first row. The most robust configuration for 500 kilohertz is going to occur at the last row. This would be with the QAM level of 32, channel coding overhead of 18%. And even with that, you get about 1.8 megabits per second for user data rate, which is good enough for one linear uncompressed audio channel and E2X stream. So let's look at the services section now. HD-Link can transport up to two stereo channels with configurable format, linear order, both those channels as linear or both of them as compressed, or combination of linear or compressed, depending on how much channel bandwidth you have and how much capacity you are able to send over the RF path. Or you can order the system without any stereo cards, which is what we refer to as an all IP system. In that case, all of your service traffic originates from outside and uses the Ethernet service, and the entire modem capacity for Ethernet service. So it's completely configurable how much total user capacity is allocated for audio versus Ethernet. So besides E2X traffic, the Ethernet services can also transport IP link codec streams. Both audio and analog digital FM MPX can be sent across the HD link. And there are a couple of reasons why somebody would use IP link with an all IP HD link system. One of the use cases SFN over 950 megahertz STL link, and the other one is to transport more than two stereo channel. IP link supports new audio compression algorithms such as AAC-HE, Opus, which requires significantly less data rates than aptax, which is what HD-Link supports. And as a result, using one of those formats, the user can easily transport more than a dozen audio channels through HD-Link. The two G722 mono channels are built into the system, and they are always available for use, even in an all IP model. So we looked at the RF and the modem section. We talked about the different services, and now we turn to the transport section. So besides the RF path, the HD Link has an additional network port, which I'm showing here as Net 2. This is in addition to the network port that is used to ingest E2X and other IP traffic from on the studio LAN. So this network 2 port can be connected to any wide area network technology such as DSL, cable modem, or unlicensed microwave for IP path. It doesn't matter which technology you use as long as there is Ethernet connection. And depending on the quality of the IP path, it can be set as the main path and the RF as the backup path. But in most cases, we have seen so far, it's the other way around. That is, the RF is the main path. And when that fails or degrades, the services can be failed over to the IP path. But the IP connection quality has been improving of late, and therefore we expect to see more of the other use case as well. And if you have a full duplex IP path, in most cases you do, the return portion that is from the receiver to the transmitter is used to report the receiver performance statistics matrix, such as receive level, signal to noise ratio. So they are available at the transmitter and web interface. It's very convenient, and then the transmitter can also take some actions based on that. So the HD Link also integrates a patented algorithm that not only supports failing over from the main path to the backup path, but also has the ability to automatically adjust the modem settings based on the reported signal to noise ratio from the receiver. For example, if the signal to noise ratio degrades, the transmitter can be configured to shut off some non-critical services using an alternate backup service profile, which in turn reduces the user data rate, thereby reducing the QAM level to stabilize the RF link. And we'll look at this use case a little bit later. Another capability of the HD Link's dual path feature is the ability to individually configure the transport path for each service, and there are a total of 5 services. Each of the two main channels are separate services, and Ethernet. The Ethernet is also a separate service, and the two G722 are separate services as well. So each service can be individually mapped to a path selection. For example, you can set them to send them on either RF or an IP path without any failover, or send them on RF as a main path and failover to IP, which is the most common case. Alternatively, if the IP path is your main path, you send it over the IP and failover to RF. And if RF and IP path capacities are always available, the best option is to send those services simultaneously on both the paths for minimal disruption. And the last bullet basically indicates what I mentioned before, that the performance data from the receiver can be used by the transmitter based on the user configuration to automatically adjust the modem setting to stabilize the RF link. So, we'll look at, a couple of the most common failover scenarios. There are a lot more scenarios that are documented in the application note and in the manual. So in this use case, all the services are sent over the RF path as shown here with the path mapping. The IP path is only used to receive performance data from the receiver. In other words, the IP path does not have the capacity to send any of the services. It only has enough capacity in the return direction to receive telemetry data. So in this scenario, there are two service profiles. The main profile is what we see here, where all the services are active, which results in 256 QAM level. And as long as the signal to noise ratio is above the user configured threshold, in other words, the RF link is in good condition, the main profile will be active. When the RF path degrades based on the signal to noise ratio value, the backup service profile is switched in at the transmitter end, which shuts off the main channel 2 here, as you can see, and also shuts off the auxiliary channel 2, which in turn reduces the user data rate requirement, and in turn also reduces your QAM level down to 32, which means that you reduce your signal to noise ratio threshold by almost 10 dB. So this is another use case. So in this scenario, both RF and IP paths are available for service transport, and there are a couple of options here. The services can be set, to send over the RF path by default with the failover to IP, and is always available for transport. The capacity is always available to transport. Then the services can also be set to RF and IP path. So you have two options here depending on the state of the IP path. When you're setting the services to RF and IP path, the transmitter will actually make copies of the packets of the service and send them simultaneously over the RF and IP path, so they are available at the receiver. So when the RF path fails, the services continue on the IP path, sending them obviously simultaneously. As I mentioned earlier, reduces the interruption time almost negligible. It's not hitless, it's not like stream splicing, but it is done with the least minimal disruption. So we covered two most common use cases. As I mentioned earlier, there are many other scenarios and settings that may apply to your scenario. So please refer to the application note and the manual that covers the different use cases. An option currency on the HD Link transmitter. This is accomplished using the main alt controller product. The RF outputs from the main and the standby unit controller, along with the status signal. The controller provides the failover logic using the control leads back to the main and the standby system. And with the redundancy configuration, the Ethernet port that is facing the studio LAN side, which is also labeled as HD port. This is a port that's used to ingest your E2X traffic and other traffic, such as your IP link audio codec streams, etc. So we want the operation to be seamless after a failover. In other words, the network elements such as your exporters and other devices should continue to send to the right HT link. And as a result, those HT ports addresses are same on both the main and the backup. And because those IP addresses are same, the HT port on the backup is kept in disabled state until it becomes active. Also, the PA on the backup can be kept in standby to consume power until the failover occurs. You can also set it up for a periodic self-test. The redundancy on the receiver is handled slightly differently. The main and the backups are connected using a crossover cable, and the logic for redundancy is actually built into the software of the HT Link receiver. The audio from the main and the backup is connected to an external audio switcher. Broadcast tools is what we recommend. The contact closure from the backup unit actually controls the switching between the main and the backup audio, and the IP path, which is accomplished using the second network port. That network port does have unique addresses on both the main and the backup, and the IP path has to converge after the failover happens without any user intervention, and the redundancy logic actually accomplishes that. So one of the key points is that either when the transmit side failover happens or switchback happens, or the receive side failover or switchback happens, the software automatically converges the IP path addresses without any user intervention. So for a multi-hop system, as I mentioned earlier, there is an option for repeater configuration for the middle system. The repeater is an all IP system without any audio cards. The service data is transferred from the middle receiver to the middle transmitter over the local network. The IP path of the multi-hop system is always end-to-end from the studio side transmitter all the way up to the last receiver. You can also order the middle system with audio encoder and decoder cards if you wanted to insert some service program services or drop some service program services. So it's completely configurable and up to the user how you get the middle system. The alarms from the middle system can also be relayed back to the studio via the end receiver system. So they are sent in-band over the second RF path and sent over the IP path to the studio end. Just a quick summary of the control and the management. HT Link supports web, front panel, and SNMP to configure and monitor the system. There is a packet filter on the transmitter to only send selected Ethernet packets from the studio LAN across the STL. This filter prevents unwanted LAN traffic to get over the RF link and use up the bandwidth and impact your audio services. There is also a built-in firewall with the IP addresses and protocol filters to prevent unauthorized access. We do realize that in some cases the systems are exposed to the public internet, especially the receiver at the transmitter side, and this capability helps guard against illegal access or hackers. There are also analog contact output monitor ports on both the transmitter and receiver. On the transmitter, there are two ports that monitor the forward power and the reflected power, and the receiver those monitor the receive level and the signal to noise ratio. The software on the system is field upgradable remotely with minimal downtime, and if you don't have an internet access at the receiver, and in some cases you don't, any changes in the services or modem is automatically adapted by the receiver or the in-band RF control channel. So for example, if you change the sample rate of an audio channel, the receiver's decoder will automatically adapt, or if you change the QAM level of the channel coding over it, everything is automatically adapted without the need for a internet path. So at this point, we'll go ahead and look at the web interface briefly to show how some of the things are configured. Okay, let's take a quick look at the web interface for HT Link. when you log in on the transmitter side, this is the landing page or the home page. This is the program services page. This is where you would configure the settings for the various services. But if this is the first time that you are logging on to the HD Link system, you would want to go to the radio link page. This is where you would configure the center frequency. That's the first thing you would configure, the one that's licensed to you. You select the channel bandwidth that's been licensed to you. You would select the output power of the amplifier. Once you select the output power, the system will provide you the status of the radiated power out of the system, the reflected power, VISWAR, and you can change any of the alarm thresholds for generating any SNMP traps for those forward power and reflected power alarms as well. So once the RF profile has been set, you would go back to the program services to select the services parameters that you want to transport. This section here, audio 1 and audio 2 are your main channels. These are the two slots that are available in the HD Link system. So in this particular system, audio 1 slot has a linear channel, audio 2 slot has the compressed card. The G722 channels of 2 mono G722 channels are on the right here, and again, there is not a lot of settings for the G722 like we have for the main channel 1 and 2, but for G722 you can turn on, turn off those channels. In this case we have turned them off, and you can set the levels for the G722. For the main channels though, you can modify the sample rate, the sample width by clicking on the modify button. This section here shows you the status of those channels. HD stream bandwidth is your Ethernet data rate that you configure as part of your services. Even though it says HD stream, essentially it carries all types of IP, in fact all IP packets, the ones that you selected, and then we'll see how exactly which ones you select on the STL access list. So you can select you can select the HD bandwidth from 0 all the way up to 3.2 megabits per second, which is the maximum capacity of the HD Link system. Depending on whether you have an all IP system or you're only transporting E2X. So in this particular case, we have selected 320. So once you have the service parameters set, you click on submit configuration. That will update the total bandwidth that's required for that for these services to go over the RF link or the STL for that matter. So in this case, the total user data rate requirement is 1.69, and if you go to the radio link, the system has selected QAM level of 32 and the coding rate of 0.8. So this is going to be very robust configuration of the modem. If you change the HD bandwidth, for example, to 1024, you'll see that the RF bandwidth has now requirement, or the data rate requirement, has gone up to 2.4 megabits per second. If you apply this to see what QAM level the system selects, again it's going to select the most optimal QAM level for you. We'll wait for the system to compute that. Okay, so it has done that. Now if you go to the radio link, you can see that the QAM level is now updated to 64, and the coding rate was selected based on the QAM level. So going to the path redundancy page, this is where you would configure the settings for the path mapping and the IP path. So on the transmitter side, we allow you to actually configure a separate selection for the forward IP path and the return IP path. In most cases, it's going to be full duplex because you get a DSL or a cable modem is going to be in both direction. But earlier on, we used to see cases where the IP path was also another terrestrial radio, which only had a forward path. But in this case, in the lab system here, we have selected both the forward and the return path, which is what we typically see now. So you select that, you type in the IP address of the WAN
port of the receiver. So this is the receiver. Since this is a transmit system, this is the IP address of the receiver over which the IP path will be connected to. And once you configure this on both sides, they will start exchanging messages, and the status will show you exactly what the forward and the return path is. So this means that the messages are getting exchanged, and when the message do flow, you will see the signal to noise ratio and receive level performance metrics populated on the transmit side. This is coming from the receiver, by the way. This section here, you would set up the primary path. So in this case, we selected RF path, but you can also select IP path as well. And here is where your service to path mapping occurs. So in this particular case, we selected main audio channel 1 to go only on the RF path. You have other choices as well. So when the RF fails, this channel will basically disappear. Will not be on the air. Audio channel 2 is selected to go on RF and IP path, and this is the compress card. So this is going to be sent simultaneously by the system on both those RF and IP link, and it's going to use up 256 kilobits of data rate. This is a linear card, as we saw. So it's with 32 kilohertz sample rate and 16-bit sample size. It takes a little over 1 megabits per second of the RF bandwidth only. Ethernet service is also mapped to RF and IP path. Again, we just changed it to 1 megabits per second, and it's going over RF and IP path as well. Now, the Ethernet data rate that you configure is going to be policed by the system. In other words, system is going to be continuously measuring the Ethernet traffic coming in to the HD Link transmitter system, and it's going to cap its use at 1 megabits per second so that it doesn't impact the capacity of your audio channels. Aux channel 1 and 2 are turned off, and therefore their bandwidth usage is 0. So talking about the selection of the Ethernet traffic, that's done through the STL access list, as I was talking about. So the STL access list selects which IP flows actually get to go over the RF path or the IP path for that matter. And in this case, we selected one IP flow, and you select it based on source and IP addresses of the packets coming in. So this could be this source IP address could be your exporter. For instance, this could be your exciter, and you can add additional flows, the ones that you want to transport over the link. This access list is the firewall that I mentioned earlier. This is to protect your web and SNMP access in case your HD Link system is exposed to public internet addresses. So that's just a brief overview of the web interface. The receiver side is exactly same or similar, and it's in fact simpler to configure the receiver system.
HD Link RF and modem performance is backed by 5 watts of power and LDPC channel coding. It's 56 QAM level for higher data capacity. Got a very flexible service configuration with option of using IP only mode in conjunction, and we talked about the scenarios where this is very useful and beneficial. And it's got a patented transport algorithm which provides reliability of services using both RF and IP path. So that concludes the presentation. We'll take any questions that you might have at this time. So the IP path of HD Link does not support hitless operation, meaning it's meant to do a hard switch. So even when you set the paths to both RF and IP, the receiver will only switch to picking up packets from the IP path only when the RF path packets stop coming in. So it's not a hitless operations similar to what we see with IP link stream splicing. So if you have a situation with several intermittent RF dropout, the best solution is to use combination of IP link and HD link and use stream splicing over both RF and IP path. So this will provide a true hitless and seamless operation in all conditions, because you're using both those paths simultaneously at a packet level. If you lose some packets on the RF, you have it on the IP. If you lose those packets on the IP, you have it on the RF. On top of that, you can use time diversity of IP link. You can use very strong forward error correction. So it opens up a lot of reliability tools which are not present in HD Link, especially for a use case such as this. In addition, you can also use live look now to monitor your RF path exactly how it's been performing. No, it's a separate system, so it's a separate receiver, a separate transmitter. Again, it's just a configuration of the software that makes it different, but the units are exactly the same. So if you had asked me this question prior to introduction of MPX IP Link MPX P codec, which we introduced last year at NAB, the answer would be no. But with the MPX P codec, we have added the capability to reduce the data rate requirement for both AES 192 and analog MPX signal to as low as 1.64 megabits per second. And even if you add additional 300 kilobits for HD radio Z2X streams, you'd be operating, at the most robust setting of 32 QAM. So the answer now is not only yes, but you can do it with a reliable setting of the RF link. The 950 megahertz frequencies are only licensed in studio to transmitter direction. If you want to have an RF technology for a bidirectional path, you would have to use some other microwave technology, and that would be the IP path. So one of your path has to be the forward 950 megahertz STL path, and the return or the second IP path can be a microwave or a wired IP connection. I hope I answered that question. If you use HD Link's service configuration, as we talked about, it can support two main audio channels. Those are stereo channels that can be also configured as mono. There are two G722 channels that are built in. There are 7.5 kilohertz channel. So if you look at just the audio capability of the HD Link itself, you got up to two stereo channels that can be configured as the main channels, and then you got the two G722 mono channels. And if you need additional capacity, as we talked about, you can add IP link over the Ethernet services, as many as you want, because you can use those advanced compression algorithms. Well, I shouldn't say as many as you want, but you can add quite a few of them because of the advanced compression algorithm that take up close to 128 kilobits of data rate. So yes, you can absolutely scale the number of channels now with the use of IP link along with HD link.